We're now going to consider sketching graphs of trig functions that involve amplitude, period, and phase shift changes. So let's first of all take a look at what we mean by an amplitude change for a trig function. Let's recall that the graph of the sine function has an amplitude of 1 and a period of 2 pi. So recall what that means. Down here we have the graph of the sine function, the red dotted curve. That is the graph of our regular sine function. And notice that it goes from -1 to +1 on the y-axis. So those are its minimum and maximum values. Now if we take the sine function and we multiply it by some constant a, that will introduce what we call an amplitude change. So for example, if we consider the graph of the sine function, that is the red dotted curve down here, and then we take it and we multiply by 3. What's the 3 going to do to the graph of the sine function? Well, anytime the sine function is 1, obviously 3 times 1, that's going to be 3. So you see how it pushes the graph upward, so its maximum amplitude is now 3. The blue curve, by the way, here is our graph of 3 sine x. And also wherever the sine function is -1, when we multiply 3 times -1, obviously that's going to give us -3. So you see -3 here on the y-axis, +3 up here on the y-axis as well. And so anytime we multiply by a constant a, that's just going to change the height of our sine function, and we call that an amplitude change. If the a happens to be negative, it will actually flip this graph about the x-axis. So if we had a -3 here, that would just take this graph and flip it so it would look like this. So that's what the -3 would do. Now let's take a look at what we mean by a period change. So to explain the concept of a period change, consider the graph of the function y equals sine x. Now you notice that this function has a period of 2 pi. Now that means that its graph starts repeating every 2 pi units that you move on the x-axis. For example, down here, the red dotted graph right here, that is the graph of y equals sine x. Now you notice when we start at the origin, when x is 0, if we go 2 pi units, the graph will start repeating again. So sine x repeats every 2 pi units, and we call that its period. Now consider a function like y equals the sine of b times x. So we replace the x in here with the b times x. The question is, what is the period of this new function? How long does it take to start repeating? Well, if we consider the graph of sine x, this function will start repeating whenever the x reaches 2 pi. If we start with x equaling 0 and we go to 2 pi, that's when this function will start repeating. Well, the same is true for this. It will start repeating whenever what is inside the parenthesis here reaches 2 pi. So if we set b times x equal to 2 pi and solve this equation for x, that will tell us how long it takes for this function to start repeating again. And solving this for x, we simply get, and that tells us our period for the function sine of b times x. And just in case the b is negative, technically we would take the absolute value here, and that's actually our definition for a period change. So it's going to be 2 pi divided by the absolute value of b, where b is the constant that is being multiplied against the x here. So let's take a look at this example down here. So here we have the graph of two functions, y equals the sine of x, and y equals the sine of 2 times x. Now the sine x, that's the graph of the dotted curve right here. And sine 2x, that's the graph of the solid blue curve. Now you notice, if we were to find the period of the sine 2x function using this formula up here, we would get that the period of sine 2x we obtain that the period is 2 pi over 2. The b is 2 in this case. This is our b. And so we just get pi for the period. And if we look at the graph of the blue curve, we see that it takes pi units to repeat. So in the blue curve, if we start at 0 and we go from 0 to pi, right there, we see we just start repeating again. And so you see the graph does verify that the period of the sine of 2x is equal to pi. Now next, let's take a look at the concept of a phase shift. So here's our definition for a phase shift. If we let c be a positive number, if we're given the graph of y equals sine x, you notice that the graph of y equals sine of x minus c will be shifted right c units, and y equals the sine of x plus c will be shifted to the left c units. That's a concept that we ran into before. Remember, if you're given the graph of a function like y equals f of x, and you consider the graph of y equals f of x minus 2, this function will be shifted right by 2 units, comparing it to the graph of this one. So the graph of f of x minus 2 you obtain from the graph of y equals f of x by shifting to the right 2 units. On the other hand, if you consider y equals f of x plus 2, this function will have a shift to the left 2 units compared to the graph of the original function y equals f of x. So this leads us to the following definition then. If we're given the function y equals sine of x minus c, we call the value c the phase shift. Notice it has to be in the form x minus c. So for example, let's consider the graph of this function y equals sine x and y equals the sine of x plus pi over 4. Now the graph of sine x is the red dotted curve right here, and the blue solid curve is the graph of sine of x plus pi over 4. Now you notice that to get to the graph of sine of x plus pi over 4, we simply take the graph of sine x and shift it to the left pi over 4 units. You notice, for example, if we go from this peak to this peak right here, this distance, that distance right there is pi over 4. And to see that a little more clearly, if you consider down here on the x-axis, notice that the graph of sine x passes through the origin. That's where x is equal to 0. And the graph of sine of x plus pi over 4, that crosses at negative pi over 4 right there on the x-axis. So we had to shift left pi over 4 units. And so we would say then that the phase shift for this function is going to be negative pi over 4. You notice that if we compare this to what we have right here, we have to really write the x plus pi over 4 as and so you see that our phase shift is really the negative pi over 4 part right here. And so that example illustrates the concept of a phase shift, or sometimes you hear it referred to as a phase change. Now let's take a look at an example that puts all of these concepts together. So to summarize what we've just considered, if we have the graph of a function like y equals a sine bx minus c, in order to pick off the amplitude, period, and phase shift, we would rewrite it like this. We're going to take the inner part here, what's inside the parentheses, and factor out a b. And what we get is this: a times the sine of b times x minus c over b. And now we can pick off the amplitude, period, and phase shift like this. The amplitude of this function is just going to be the absolute value of a. The period is going to be 2 pi over the absolute value of b. Just in case this b is negative, we take the absolute value of it. And the phase shift is going to be the c over b part. So that's how we pick off our amplitude, period, and phase shift. We just have to rewrite it in this form right here. And this is also true for the cosine function as well. Now let's take a look at this example. Let's sketch the graph of y equals 3 times the sine of 2x plus pi. Now let's first of all pick off the amplitude, period, and phase shift. So what we're going to do is we're going to rewrite this as follows. We have it written down here, but let me just show you. We're going to take this 2 right here. That's our b. And we're just going to factor it away from the 2x plus pi. And what we end up with is this right here. So we're going to get 3. Alright, so that's what we get when we factor the 2 away from the 2x plus pi. So we get 2 times x plus pi over 2. And now we can easily pick off our amplitude, period, and phase shift. Our amplitude is going to be the 3. That's going to be our amplitude. Our period is going to be 2 pi divided by the b. That's our b right there, the 2. So 2 pi over 2, that equals pi. So there is our period. And then our phase shift is going to be negative pi over 2. Notice it's negative because we have to think of this as being x minus negative pi over 2. And so that's going to be our phase shift. So we're going to be shifting to the left by pi over 2 units. Now let's sketch all of this by hand. So what we have to do here, we're going to start out with the graph of sine x. So remember, the graph of sine goes something like this. Okay, so there's the graph of sine. Now let's introduce an amplitude change of 3 units. So then our graph would go like this. Okay, so right here we have the graph of Now let's introduce a period change. So we're going to put a 2 right here in front of that x. And that's going to change the period to pi. So what we have to do is basically compress this graph. So instead of repeating every 2 pi units, it repeats every pi units. And then we would have a graph that looks like this. So that is a rough sketch of the graph of three times the sine of 2x. Now what we have to do is replace the x with an x plus pi over 2. So that's going to shift this graph to the left pi over 2 units. So if we look here, this point right here, if we shift, that's at pi over 2 on the x-axis, so this actually has to get shifted to the origin for the next graph. And so our final graph is then going to look like this. And this is a very rough sketch of y equals And that's what we wanted to sketch the graph of. So you notice how we took it in stages. We first of all changed the amplitude, then we changed the period, and then we did a phase shift to the left by pi over 2 units. And let's just see what how the computer graph compares to what we have down here. And so right here we have a computer graph of and you see that does look exactly like what we had sketched. Notice that we start here at the origin, we go down to -3, cross at pi over 2, up to 3, down, so we have a complete period here from 0 to pi with an amplitude of 3, and then we just start repeating again. And the red dotted graph, that's the graph of our original sine function. And so that's how you could graph something like y equals the sine of x with an amplitude, period, and phase change. Graphing something like the cosine would be exactly the same, except you would start with the graph of the cosine function instead of the graph of the sine function, so it would look a little different. You could also graph things like the cosecant and secant functions in similar manners. The graphs of tangent and cotangent, we don't have an example covering those exactly. They would be a little different because the period for the tangent and cotangent functions are pi instead of 2 pi.